We are going to continue our discussion on the Morse-Mail complex by talking about an extension of Morse theory to a discrete setting. We will notice that while this extension is to a combinatorial space, it plays an important role in the computation of the Morse-Mail complex for piecewise linear functions. We will begin by talking about some issues that plague the computation of Morse-Mail complex for piecewise linear fields. We have discussed them earlier in previous lecture. I will just recap that. And following this discussion, we will move on to analogous structures to what we have studied earlier, both in the discussion of Morse functions and in the discussion on Morse-Mail complex. So you will notice a lot of parallels between the previous lectures and this current lecture. So we will look at a discrete equivalent of the gradient. We will look at a discrete Morse function, although I will not define that explicitly. We will talk about a discrete gradient field and use that for all practical purposes to talk about the discrete Morse-Mail complex. Finally, we will talk about an extension of the notion of critical point pair cancellations to the discrete Morse setting. In previous lectures on the Morse function and the Morse-Mail complex, we have started the discussion often with the focus on smooth functions that behaves quite well, where the gradients are always well defined. We quickly noticed then that while moving to the piecewise linear setting, several of the assumptions that we made for the smooth functions are no longer valid. For example, the gradient is not necessarily defined everywhere, and more commonly so in the case of piecewise linear functions. We noticed that the critical points may not be simple. We talked about the presence of multi-saddles. The classification of critical points is not as easy as in the case of the smooth function, primarily because of the presence of flat regions where it is not clear how to consistently declare one point as having higher function value than the other. And such a critical point classification was central to the computation of the Morse-Mail complex. Further, while talking about the Morse-Mail complex, we also noticed that due to the piecewise linear approximation, there were many situations where the gradient lines would merge or split depending on the direction in which they are traversed. This makes it difficult to ensure transversal intersection between the ascending and descending manifolds. We also discussed one approach where triangles were split in order to ensure this, in order to avoid transversal intersection. We will follow a completely different approach in this lecture by focusing on a discrete variant of Morse function. So this discrete variant was introduced by Robin Forman. As always, this new theory was developed with a completely different purpose in mind, namely to prove analogs of results from smooth spaces to combinatorial spaces. So Robin Forman extended Morse theory to combinatorial spaces such as simplicial complexes or a collection of cubical cells, namely a cubical cell complex. We will focus our attention only on these two complexes. Morse theory, Forman's version of discrete Morse theory, works for general cell complexes. So this is the space on which the function is defined. The function in itself is also discrete, namely that the scalar function is defined on all cells of a simplicial complex. While we will not be able to cover Forman's discrete Morse theory in detail, here is a reference that you can use to understand this theory better. So this write-up is a general introduction to this discrete extension of Morse theory. What we will do in the following slides is to focus on those aspects of Forman's discrete Morse theory that are relevant and necessary for introducing the notion of Morse-Mail complex and leading to a simple and fast algorithm. In the discussion on Morse functions, we began by talking about gradients and then discussed the definition of a Morse function. Different from that, we will not talk about the discrete Morse function explicitly in these slides. The paper that I give you as reference does contain an explicit definition of the discrete Morse function. What we will do is to focus on the notion of gradient, similar to our earlier discussion on Morse functions. So like I mentioned, we will begin by talking about gradients, and we will notice that this is sufficient for us to discuss the various concepts that are required to define the Morse complex and the Morse-Mail complex. In the smooth case, we talk about a gradient. In the discrete case, where a function is defined on cells of a combinatorial space such as a cubical cell complex, we talk about gradient pairs. So let's try to define a gradient pair. First, we will begin with a definition of what is called a discrete vector. So let's consider this on the right. Let's consider this simple cell complex. This is a cubical cell complex in 2D, which consists of 0-dimensional cells that are nodes, 1-dimensional cells that are arcs, and 2-dimensional cells that are these squares. The collection of these cells satisfy the same properties as the simplicial complex. So we refer to the nodes, arcs, and the squares as 0, 1, and 2-dimensional cells. So in general, for k dimensions, we can talk about k-dimensional cells and faces and cofaces of these cells, similar to the simplices and the simplicial complex that you have studied earlier. So in this simple two-dimensional cubical cell complex, a pair of cells sigma sub k and sigma sub k plus 1 form a discrete vector, which is denoted using this less than symbol. So sigma k plus 1 forms a discrete vector when we pair the node with sigma sub k with the edge sigma sub k plus 1. This vector has a direction that is directed towards the higher dimensional cell. So you notice that the discrete vector is between a pair of cells that differ in dimension by 1. These two cells are incident on one another. So namely, one of the cells is the face of the other, and the discrete vector is directed from the lower dimensional cell to the higher dimensional cell. A collection of discrete vectors forms a discrete vector field. So a discrete vector field satisfies one property. So namely that any cell is does participate in only one pair. So namely, if we have a collection of vectors between the 0-dimensional and 1-dimensional cells, we will call it a discrete vector field if every edge and every node participates in exactly one vector. Such a collection of vectors is called a discrete vector field. Let's say capital V. A V path in the discrete vector field, we could use this smaller case V. A V path in a discrete vector field is a collection of vectors that is an equivalent to the integral line in the smooth case. So how is this defined? A V path, let's show a V path in this cell complex. So here are a collection of gradient discrete vectors. So this collection of discrete vectors, let's give them names, that begin with a node. So let's call that alpha, and with an index with running index 0, and dimension in general k. Here the dimension is 0 because it's a vertex, followed by beta, which is the first in this path, and the dimension is k plus 1, followed by alpha sub 1, again dimension k, beta sub 1, dimension k plus 1, alpha sub 2, dimension k, beta sub 2, dimension k plus 1, and so on until we reach a target which is, let's call it alpha sub r dimension k. So a V path is an alternating set of nodes and arcs, or arcs and two cells, which satisfies the following property. Alpha sub 0 and beta sub 0, or alpha sub I and beta sub I, that are adjacent to each other form a discrete vector, and any two alpha and beta that are adjacent to each other in the path are satisfy a phase cophase property. So namely, alpha sub 0 is a phase of beta sub 0, which is obvious, but alpha sub 1 is also a phase of beta sub 0. So you can quickly see that this V path captures the notion of an integral line, or it is at least similar to an integral line. The next concept that we want to introduce is a gradient path. So far we have been talking about generic paths between any pair of nodes that follows the discrete vector. Now if this V path does not contain any cycle, then we call it a gradient path. Right? So that's kind of intuitive. We want a monotonic path that strictly goes in one direction. There are no cycles. Such a V path is called a gradient path. Any vector within this gradient path is called a gradient pair. So for a moment, if we imagine that the entire collection of vectors that I am showing here are do not contain any cycles, then every pair is a gradient pair. So note that the gradient pairs need not be only between nodes and arcs, they can be between arcs and two cells as well, such as here. Right? So there are two kinds of gradient pairs possible in a two-dimensional cubical cell complex, namely the node arc pairs and the arc two cell pairs. A discrete vector field V becomes a gradient field V if all the V paths in this discrete vector field are gradient paths, namely if there are no cycles in any of the V paths within the vector field. So this makes sense, and it's analogous to the gradient lines that correspond to a smooth function. So what we have seen now so far is an extension of the notions of a gradient field to the discrete setting. Moving on, let's look at critical points and their equivalent concepts in the discrete Morse theory setting. Recall that a gradient field is a discrete vector field which does not contain any cycles. So there are no closed v paths. Of course, there can be a trivial closed v path which is of length 1, but we are talking about non-trivial closed v paths here. A critical cell is a cell in the cubical cell complex which has no pair. So this is analogous to the notion of a zero gradient in the smooth case. So let's try to recreate the set of vectors that we saw earlier, and you can try and see which cells are critical. So I have the 0, 1 gradient pairs and the 1, 2 gradient pairs. This leaves a few cells unpaired. What I have drawn is a specific gradient field. So I happen to design this gradient field in order to illustrate the various concepts necessary for this lecture. So you can quickly see that designing such a gradient field is also a non-trivial task. Okay, so let's come back to the discussion about critical cells. Here is a two-dimensional cell which is not paired with anyone. So this is critical. We also have a node here which is not paired with anyone, hence critical. And if you notice, there is a single edge here which is not paired with anyone, and hence that one cell is also critical. So in the smooth case, we have the notion of index of a critical point. The index of a critical cell is simply the dimension of that cell. So the 0 cells that are critical correspond to minima. As you can see, these are minima. The one-dimensional cells that are critical are our saddles, and the two-dimensional cells that are critical are the maxima. Let's see if our intuition also transports the ideas, right? So in the smooth case, we know that in the neighborhood of the maximum, all the gradient lines have to flow outwards. That seems to happen even in this case. In the neighborhood of the maximum, all the gradient pairs seem to point outwards. In the neighborhood of a minimum, all the gradient pairs seem to point inwards. Right? So here the direction of the gradient pair indicates upward function value or downward function value, as the case may be. So both conventions are quite common in the literature. The saddle has gradient pairs that satisfy the property of alternating in inward and outward arrows. More crucially, it's important to note that the max which has Morse index 2 is a 2 cell, the min which has a Morse index 0 is a 0 cell, and the saddle which has Morse index 1 is a 1 cell. That is the crucial structure that we want to note and use. Let's move on to the discussion about collections of integral lines. In order to define the Morse complex and the Morse-Mel complex, we had earlier talked about a maximal integral line. So namely, an integral line that you extend until it cannot be extended any further. So these maximal integral lines have an equivalent in the discrete setting, which is a maximal gradient path. A collection of such maximal gradient paths define an ascending manifold. Similarly, a collection of maximal gradient paths also define a descending manifold. Let's take the example of a maximum from the example that we saw earlier. The collection of V paths that originate from this maximum downwards, namely, should constitute the descending manifold of this maximum. So this would be given by the V paths shown using these three gradient pairs. The ascending manifold, for example, for the minimum that we saw in the lower right region, consists of all the V paths, all the gradient paths that happen to flow into this minimum, such as this direction. Right? So we also know that there is a saddle here. So these V paths do connect the critical points. Recognizing these connections is crucial for computing the Morse complex and hence the Morse-Mel complex. So you can already imagine how one can compute the Morse complex using the discrete extension of Morse functions. We design this discrete gradient field, and once we design the gradient field, the ascending and descending manifolds can simply be computed via path traversals in a graph. So several existing algorithms that employ the discrete Morse theory approach do use graph algorithms for computing the Morse complex and the Morse-Mel complex. But rather than talking about the algorithm now, let's talk about some properties. We note that the descending manifolds and the ascending manifolds can never intersect. For example, the two 1-2 paths from the maximum can never intersect the 0-1 paths that flow towards the minimum, just because they are working on two different collections of objects. So the property of no transversal intersection is satisfied by definition. Now, like I mentioned, these V paths, gradient paths here, do connect the critical points, right? This gives us the combinatorial structure of the Morse complex and hence the Morse-Mel complex. For example, we can see that the saddle on the lower left connects to the maximum. The saddle also connects to the minimum, that is the descending manifold. Let's try to draw that here. The saddle via a second route connects to the minimum, that is also a descending manifold. The first manifold that we drew was the ascending manifold from the saddle. So with this we have the combinatorial structure of the Morse-Mel complex. We have all the connections between the saddle and the max and the saddle and the min. So hence we have the Morse-Mel complex. So note that the two cells of the Morse-Mel complex can also be computed explicitly by tracing the 1-2 gradient pairs. Finally, we want to talk about cancellations. So let's look at one of these combinatorial connections, namely from the saddle to the maximum. There was a V path. It's a very simple V path that connected the saddle to the maximum. In the smooth case, we talked about critical point pair cancellations and how they can be used as an atomic operation to generate a smooth function from a Morse function f. How do we implement cancellation in the discrete Morse setting? Let's look at this pair, the saddle maximum pair that is connected via a gradient path, in this case a single gradient pair, but you can imagine that there are situations where this path consists of multiple gradient pairs. A cancellation is essentially a reversal of the V path. So all the gradient pairs that lie along the gradient path connecting the saddle to the maximum may be reversed in order to cancel this pair. Now reversing this direction will essentially introduce a pair for both for the maximum, erstwhile maximum, and the erstwhile saddle. Hence they will no longer remain critical. And this reversal will not introduce any new cycles as well. So hence the resulting discrete vector field will continue to be a gradient field where the previous gradient path between the critical points is now reversed. So cancellation can be implemented via this simple v-path traversal. While the process appears to be simple, once we go into 3D, there are a few situations, especially for gradient paths between a one saddle and a two saddle, where the v-path reversal is not a trivial problem. In fact, there may be situations where the v-path reversal may not be possible. So in those cases, we have to circle back to the combinatorial structure of the Morse-Mel complex and look at a simplification of the combinatorial structure via removal of critical point pairs. So these cancellations may not be always realizable via v-path reversals, whereas in 2D one can always do a reversal. So with that, we come to an end to the discussion on the discrete variant of Morse theory and how it extends to the definitions of Morse complex and Morse-Mel complex. So just to recap, we talked about gradient pairs. We saw that the gradient pairs can be between nodes and arcs. They can be between arcs and two cells. We talked about v-paths, alternating sum of, not alternating sums, alternating alternating cells in terms of dimension. These v-paths could be in higher dimensions as well. A collection of v-paths that does not have any cycles is called a gradient path, such as what is shown here, and a collection of such gradient pairs forms a gradient field. Cells that are not paired in this gradient field become critical, such as the max, saddle and min shown here. The set of v-paths that either terminate or originate at the critical points can again be used to compute the ascending and descending manifolds, similar to the smooth case. Now, if these ascending and descending manifolds are computed for all the critical points, we get the combinatorial structure of the Morse-Mel complex. So with that, we conclude this discussion on the discrete Morse-Mel complex.